We're going to be looking at section 2.3 today. Does anybody have homework questions before we turn there? Yes.
Yeah, Fibonacci, and to understand many of the questions, just to understand the concept of the game, or the goal of how to win the game by choosing Fibonacci numbers.
Okay, so you want to review how do you win with Fibonacci nim?
Real quick, but
Okay.
The reverse, right? The reverse of the Fibonacci numbers.
Okay, so everybody write down the first, say 10 Fibonacci numbers, and we'll look at how do you win at Fibonacci nim. So we'll write down the Fibonacci numbers, and then suppose you're playing Fibonacci nim, and there's 25 toothpicks. You go ahead and put the 25 where it shows up in the sequence of the Fibonacci numbers. It shows up right here. So you pick the largest number smaller than that. So 25 is right here. So 21 is the largest Fibonacci number smaller than 25. And we make sure that we don't start with a Fibonacci number of sticks, or else you don't have a winning strategy.
Are we going over 2.2 or 2.3?
The question was from 2.2.
Okay.
So you break it up, the 25, into the sum of Fibonacci numbers. So we started with 21, and now there's 4 more that I need. So now 4 goes right here, so I say plus 3. That makes 24, so I need 1 more. So the winning strategy is to pick 1. Be the first player and pick 1 stick, the smallest number in your sum of Fibonacci numbers. Suppose we had 63. 63 sticks to start. Then we say, well, 63 is between 55 and 89, so we pick 55 to be the first number in the sum. And then how many more would we need? We would need 8. So 8 is a Fibonacci number. So I wrote the 63 as a sum of Fibonacci numbers going down, using the biggest one I could all the time, but going down. And now I would pick, as the first player, I'd pick 8. Okay. Any other questions? Yes.
It was also the soft one. From what I got was like, if you have like 5 black and 5 blue, and how many you need to get, I think, was it the most? Can't remember exact wording. Because I thought you were supposed to do like, guarantee you to get like 5 pairs of like one color. So I thought you were supposed to draw 2 more left out of, past that last number or so. I think I'm getting that wrong.
Was that in section 1.4? Wait, what assignment was that on? 2.2?
2.1.
2.1?
Or it might have been 1.
I think it was 2.1, yeah, and I in my double vision I grabbed 2.2. Okay. There we go. So if you had 5 pairs of black socks and 5 pairs of blue socks, and you wanted to guarantee a black pair, what you're doing is you're thinking, well, what if I picked all blue socks first? If I accidentally picked all blue socks first when I'm looking for a black pair, how many blue socks are there? So if you had 5 pairs, there's 10 blue socks. So think in number of socks, not pairs of socks as you're drawing the socks out. So if you had 5 pairs of each, then you'd pull out all the blue socks first, and that would be 10 blue socks, and then if you pick 2 more, those have to be black.
Okay.
So you wouldn't necessarily pick all blue socks first, but we want to ensure that we pick that. So for yours, it would have been 12.
Yeah, nice.
And I had another hand. Who else had? Yes,
Okay, so for the Fibonacci nim lines,
Fibonacci.
like, mine has like 113 sticks in it.
113
So I
sticks.
can't figure out what, like, number I'm supposed to pick first.
Okay, let's pick that. Let's work on the Fibonacci nim question with 113 sticks. So we'll go back to our
In mine, I have 1,016 sticks.
1,016. Okay. Okay, well, we'll need a longer Fibonacci sequence, right? So write out your Fibonacci sequence as long as you need to for your problem. Okay, that should be enough for both of those. So the 113 sticks falls in here, and I'll take 113 and write it as 89 plus something. So 89 plus 24, 11 and 13 to get to the 113. So 24 falls in here, so now I'm going to write the 24 as 21. And then how many do I need now? I lost track. So let me add these up. 89 plus 21 is 110. I need 3 more, and 3 is a Fibonacci number, so I'll put 3 there. And that's the number of sticks that I pick. Okay. Or if I have 1,016 sticks, the 1,016 starts here, falls here. So I'm going to put 987. Plus 29, because you need 13 plus 16 is 29. 29 falls right here, so I'm going to add 21 on. And I'm losing track again. 987 plus 21.
58.
You need 8 more, and 8 is a Fibonacci number, so 8 would be my last one I have to write down, and 8 is the number of sticks that I would pick then. Yes?
Can you use the same Fibonacci number again? So if you need 6 instead of doing 3, 2, 1, can you do 3, 3?
No, don't do 6s, 3, and 3. Okay, don't do that.
So 3, 2, 1.
Yeah, so it'd be 3 plus 2 plus 1. Actually, you wouldn't do that, would you? You do 6 as 5 plus 1. Okay. Any other questions? Okay. Okay, well, hopefully everybody feels pretty good about the Fibonacci numbers, and we will turn our attention to 2.3 prime numbers. So the author opens this with a question, 2.3, can you write 71 as a product of 2 smaller numbers? What is a product? What does product mean? What does product mean?
Multiply 2 numbers together to get a number.
Good. Product means multiplying. So go ahead and decide, or have you decided? Can you write 71 as a product of 2 numbers? What did you decide? Anybody? You might want your calculators out for today. So you would take your 71 and you decide it's not even, so you're not going to divide by 2, right? And that means you don't have to look at any numbers that are even to divide into it. If 2 doesn't divide into 71, no even numbers are dividing into 71. So we turn to 3. Does anyone know the rule to see if 3 divides into a number? Nobody learned that rule? 3 will divide into a number if you add up the digits and that sum is divisible by 3. So 7 plus 1 is 8. 8 is not divisible by 3 evenly. So 71 is not divisible by 3. That just works for 3 and for 9, which is kind of cool. Like, why does that work? You can do some algebra and think about why that works if you'd like. Okay, so no number that divides that's divisible by 3 is going to divide into 71 because 3 doesn't divide into 71. So we have 2, 3, 4 is even, forget that. 5, not 5, it doesn't end in 0 or 1. 6 is divisible by 2 and 3, so we skip that. 7, no, 71 divided by 7 is 10, remainder 1. That brings us to 8. 8's even, forget that. 71 is not divisible by 9 because it's not divisible by 3. And that brings us to big, right? Once we divide and we get a result smaller than what we divided by, then we know that we're done. Okay. So 71 is not able to be written as a product of 2 smaller numbers. What do we call that? Yes?
Prime number.
Prime. Yes, it's prime. 71 is prime. Let's write the definition out for prime. A definition, our definition is a natural number greater than 1. A natural number greater than 1 that cannot be written as a product of 2 smaller natural numbers is a prime number. A natural number greater than 1 that cannot be written as a product of 2 smaller natural numbers is a prime number. So there's some words in that definition maybe you're not familiar with. How about the word natural number? Does anyone know what a natural number is? What's in, yes?
That's not decimal.
So those would be ones that are not decimal, have a particular name too. Those are called integers. In fact, we'll be learning all of these groups of numbers throughout chapter 2. So that will be one thing you'll need to learn for your quiz. So first we'll look at natural numbers. Anybody have any other ideas of a group of numbers? Yes?
So natural numbers would be like your counting numbers, so like 1, 2, 3, 4.
Yep, perfect. The counting numbers, 1, 2, 3, 4. And that's why we think of them as the natural numbers. They were the numbers our ancestors first used naturally, just looking around and counting their flocks, or the toes on their baby's fingers, toes on their baby's feet, and so on. Okay, what about product? That'd be multiplying, right? We just talked about that. So we have a whole section on prime numbers, and the question is, why do we care? Why do we care about prime numbers? Why do we care about prime numbers? let's see, the life lesson for this section is simple observations also often have deep consequences. The prime numbers are the building blocks of all the numbers. You just saw that your number 71 was prime. So each number is either prime or it's not prime. And we have the prime factorization theorem. Leave a little space here, we'll write some other stuff there, okay? The prime factorization theorem, though. The prime factorization theorem says that every natural number greater than 1 is either a prime number Every natural number greater than 1 is either a prime number or it can be expressed as a product of primes. Every natural number greater than 1 is either a prime number or it can be expressed as a product of primes. So one reason we care about primes is that they're the building blocks of all the numbers. All the numbers can be broken down into a product of prime numbers or they are themselves prime. So we want to understand simple things deeply so that we can move forward with them. So the prime factorization theorem is one reason we would care about prime numbers. Another reason, well, it's the basis for encryption. Who knows what is encryption? It's the basis for computer encryptions. Anybody buy anything on Amazon or eBay? Anybody put their credit card out there online? Okay. Your information was encrypted. What does that mean? Is that a good thing? Do we want it to be? Yes.
It's safe, it's under a code, it has to be deciphered.
Right. It's safe. It's under a code. It has to be deciphered. So it's rewritten another way. You actually have a section in your book on that, section 2.5, about how that's done if you're interested in that. We'll look at just a little bit about how that's done. I have an article from Extreme Tech. So it turns out that finding prime numbers is quite difficult, and that's why the encryption algorithms depend on them. Finding prime numbers is quite difficult, and factoring really big numbers is quite difficult. Like we took the 71 and we found out it was prime without too much work. But if your number is several hundred digits long, even a computer has a hard time with that. Computers are great at adding and multiplying, but it's very hard for them to do division efficiently. So that's what this article is talking about. It's a website, Extreme Tech. So the article is saying, let me make it fit here. So there is a functional limit to the size of the numbers we can factor into primes. And this fact is absolutely essential to modern computer security. Pretty much anything that computers can easily do without being able to easily undo will be of interest to computer security. Modern encryption algorithms exploit the fact that we can easily take two large primes and multiply them together to get a new super large number, but that no computer yet created can take that super large number and quickly find out which two primes went into making it. So it talks a little bit about those speeds on this next page. That's not to say that there has been no progress in factoring large numbers. In 2009, researchers networked several hundred computers together and spent the equivalent of about 2,000 years for a single computer using advanced factoring algorithms to factor the RSA 768 number. That is to say, a number with 232 digits put up by the RSA group as a factoring challenge proving it was possible to break 768-bit encryption in non-universe heat-death timescales. So that was unacceptable for the security world, of course, and so now the standard is moved up from that. The standard is now RSA 1024, using numbers with 309 digits. So encryption depends on prime numbers, and the finding of a new prime number is very exciting in the mathematical community. They're not that thick. There's not that many prime numbers as we get into the bigger numbers. In fact, here on page, well, your book doesn't have pages on your ebook, but here we have a chart in this section talking about how dense the prime numbers are. So if you look at the number 10, there's 4 prime numbers smaller than 10. That proportion, then, if you take 4 divided by 10, you get 0.4. And then if you look at the primes up to 100, then there's 25 primes that go up to 100. That proportion is 25 divided by 100, or 0.25. And this proportion, as we look for primes smaller than 1 million or 10 million or 100 million, that proportion gets smaller and smaller. So you see, we started out with a proportion of 0.4 primes, and we're all the way down to only 5 100ths, from 4/10 to 5 100ths. And amazingly enough, this is what I find amazing. Gauss, he would have been around in the 1800s, and Legendre, they found that the proportion of primes approaches 1 divided by the natural log of n. Now, who even thinks like that? These men were brilliant to figure out not just the natural log function, because they probably use the natural log function a lot, but to look at the 1 divided by the natural log function and realize that that was approaching this proportion is really amazing. They actually then have a theorem regarding that, the prime number theorem. As n gets larger and larger, the number of prime numbers less than or equal to n approaches n divided by the natural log of n. Well, we're going to be looking at prime numbers, and we'll be looking at theorems too. I think first, though, the first thing is just to see if you can factor. So let's go ahead and work on that. So go ahead and factor. So think about factoring and how you'd find the prime factorization. So what is one way you could factor 70? Write it as a product. What is one way you could do that? Yes?
7 divided by 10.
Yep. So 7 times 10. I'm going to write it like this. Because then we can keep going, right? Because how can you factor 10? 5 and 2. Yeah. And then 2, 5, and 7 are each prime. So we've come to the prime factorization if we look at the ends of the branches here. This is 70 is 2 times 5 times 7. You can write that with little x's, or you can write it with the little dots, or with little parentheses. Either way is a way to show multiplying, whichever you prefer. But there is only one way to factor that if you go to the complete prime factorization. I mean, you could rearrange, like you could say 7 times 5 times 2, or 2 times 5 times 7, or 5 times 2 times 7. But you can't find another way besides those 3 numbers multiplying together. That's it. That's the only way. So if you started out saying, well, 7 is divisible by 5, it's 5 times 14, that's great. And then the 14 is 2 times 7. So any way you factor, you get the same result. How about 38? So one way is to just, when you're looking at how you can factor, one way is to just look and see if the number is even, and if it is, divide 2 out. So we'd have 2 divides into 38 19 times. 19 is prime. So 38 is 2 times 19. Here's one for you to do. Nice big one, okay? So 250. Go ahead and find the prime factorization of 250. While you do that, I'm going to hand out a little handout. These are the numbers of 1 to 100. Online students, you can print that off D2L content. So no matter how you started out factoring the 250, you should have found that 250 is 2 times 5 times 5 times 5. There's only one way to factor each number. Either the number is prime or there's one unique prime factorization. We're going to find some primes. We're going to use the method that we call the sieve. Let me get the spelling right. The sieve of Aristophanes. That sounds like an ancient name, because it is an ancient name, okay? Aristophanes lived around 276 BC, and his method for finding primes is called the sieve of Aristophanes. So what he would do is, first you cross off 1, because remember our definition? What was our definition? We're going to cross off all the numbers that aren't prime using the sieve of Aristophanes method. And our definition said we needed a natural number greater than 1. Okay, so 1's not a prime, so we're crossing it off. Two is a prime number though. And now we'll cross off everything that's divisible by 2. So just go through your list and cross off everything divisible by 2. Evenly divisible by 2. So we crossed off all the evens. And then we come to 3. You remember your rule for what's divisible by 3, right? You add the digits up. If the sum is divisible by 3, then the number itself is divisible by 3. Or you can just remember your multiples of 3. So cross off the multiples of 3. So after you cross off all the multiples of 3, So you don't have to worry about multiples of 4, because anything that was divisible by 4 is divisible by 2, so it's already been crossed off. And now we can cross off multiples of 5 though. So 5 itself is prime, but we'll cross off multiples of 5. So anything ending in 5 or 0 is crossed off. 6 is even, so we don't have to worry about multiples of 6. They've already been crossed off when we did multiples of 2. 7. Okay, hopefully you remember your multiples of 7. I remember making my daughter learn her 7s table and counting forward from 7 and back from 7. It's not a better memory that we have. But she got it. There's not an easy rule for if a number is divisible by 7 except to divide it. If you need your calculator, that's fine. Okay, so now we're down to multiples of 8, which we would have already crossed off, and multiples of 9 are crossed off, multiples of 10 are crossed off, and so we're actually not having to cross any more off because why? Why don't we have to cross any more off once we get to 10? Yeah, not in our list. Because the 10 times 10 is 100, so now if we were like looking for multiples of 11, anything that we multiplied by 11 would have been bigger than 100, or else it would have been crossed off already when like 11 times 2 is 22, so we already crossed that off. 11 times anything bigger than 10 is off our list. But now Aristophanes would have gone further, right? He was looking for all the primes, so we're just looking through 1 through 100. I'll read them off and you can make sure you didn't miss any. You should have 25. So we have 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 37, 41, 43, 47, 53, 59, 61, 67, 71, 73, 79, 83, 89, 97. And I could just double check. Well, we only went up to 100. What is the largest prime? What is the largest prime? From our chart, we know there's some that fall between 100 million and a billion. Are there any primes bigger than a billion? What do you think? What? Any ideas? No ideas, or no, they're not bigger? Once we get to a billion, can we multiply numbers together to get any number that's bigger than a billion? Well, from ancient times, we know that there is no largest prime. We're actually going to prove that in class. We're going to prove that there's no largest prime, and not only that, it'll be a proof that I would expect you to learn for a quiz. So there'll be a number of proofs that I ask you to learn throughout the semester, and I think it's a good idea to think about what is a proof and why you'd want to look at a proof. I like the definition that I found from Peng Shi at Duke University. A proof is a sequence of impeccable logic. Proof is a sequence of impeccable logic leading to the inevitable conclusion. So in mathematics, every step of the proof is predicated on the step before, and each step itself must be invulnerable. It must be absolutely accurate. Mathematicians are so committed to accuracy. I'll tell you a story about a mathematician and an astronomer and a physicist that were traveling through Scotland to show you how important it is to the mathematicians to be accurate. So these three scientists were traveling through Scotland, and they stopped by a field, and the astronomer said, "Oh, look, the sheep in Scotland are black," because there was a black sheep in the field. And the physicist turned to the astronomer and said, "No, my friend, no. Look, in Scotland there is a field with one black sheep." And the mathematician turned to them both and said, No. In Scotland, there is a field containing a sheep, one of whose sides is black, because they could only see one side. Okay, so mathematicians want everything accurate so that they can make sure they're saying exactly what's correct. So the proof then is a sequence of impeccable logic leading to the inevitable conclusion. And why would I ask you to learn to write proofs? Why would I ask you to learn to write proofs? Yes.
So we can state why the rule or the theory is usable, or why we can trust it. But
Yep.
also just test if something does apply to the theorem.
Good. So you can tell why a proof is able to be trusted and if something applies to it or not. So that's good for a specific proof. In general, this class is giving you credit for quantitative literacy and math competency. So you need to be learning the skills that we associate with that, and one of those big skills is logic and critical thinking and being analytical in the way you think things through. So I would like you to learn to be logical. So that whatever field you're going into, you're going to have to argue something persuasively at some point, and I'd like you to be able to do that. Now, there's someone famous you know who studied math just for the purpose of learning how to make these logical arguments. Does anybody know what Abraham Lincoln did before he was president?
Vampires, didn't
What did he do?
he? He hunted vampires, didn't he?
Hunted vampires. Now that I don't know about. What about?
He studied law.
He studied law. Yeah. So Abraham Lincoln went to school to be a lawyer. When he got to school and realized that he was going to have to make persuasive arguments to a jury to persuade him to his way of thinking, he set aside his lawyer studies and took up mathematics. In fact, he took up Euclid's geometry. How many of you remember doing proofs in geometry? Okay, that's what Abraham Lincoln did, and he mastered Euclid's geometry. And then when that was done, he knew he could make a reasoned series of arguments that led to an inevitable conclusion, so he felt prepared to persuade a jury at that point. So hopefully you'll get to some of those skills in our class too. So that you can have logical thinking that leads to persuasive, reasoned arguments. Okay, so here's our goal. Our goal is to prove that there is no largest prime number. Goal is to prove there is no largest prime. So we're going to think out a strategy to do this. I think I'll start a new page here. Now we start small. Okay. Remember our life lesson here was to have simple observations with deep consequences. So we're going to have simple observations with small numbers, small primes that we're familiar with, and those will lead us to bigger values. Find a prime larger than 3. Okay, someone give me a prime larger than 3. 5. Good. Okay, so we know that because we know the smaller numbers. So now we're going to add to that some conditions. Find a prime larger than 3 with a remainder of 1 when divided by 3, or by a number smaller than 3, by 2. So now I need a prime larger than 3, which has a remainder of 1 when divided by 3 or by 2. Did you say it? 7. Yeah, 7. So 7 divided by 3 is 2 remainder 1. 7 divided by 2 is 3 remainder 1. In fact, you can think of 7 as 2 times 3 plus 1. Now we're thinking this through deeply because now we're going to use this pattern and see where that takes us. Okay, so let's find a prime larger than 4. And we'll make the same conditions. Find a prime larger than 4 with a remainder. Oh no, we'll just say find a prime larger than 4. Okay, so let's use the same pattern. So when I needed a prime larger than 3, I took 2 times 3 and added 1 on. So let's take 2 times 3 times 4 and add 1 on. And what does that give you? 11. I think it's bigger than that. So maybe you need a calculator then. Anybody? 25. Okay, not prime. So the 7 was prime. 25 is not prime. What is the prime factorization of 25? What is it? Yeah, 5 times 5. So 25 wasn't prime. However, the prime factorization of 25 had a prime number 5, which is larger than 4. So this time, the 25 wasn't prime itself. However, its prime factorization contained a number larger than 4. That's because all the other numbers that were smaller than 5, the 4, 3, and 2, when they divided in, they left a remainder of 1. 25 divides by 4 6 times remainder 1. 25 divided by 3 is 8 remainder 1, and 25 divided by 2 is 12 remainder 1. So all the numbers smaller than 5, from 4 down, they left a remainder of 1. So that meant the prime factorization of 25, well, that had to have a prime bigger than 4. So this strategy of multiplying these numbers together and adding 1 will always give us either a prime number right off the bat, like 7, or it will give us a number that has a prime factorization with a prime bigger than the number we're looking at. So let's try for 5, for example. Let's find a prime larger than 5. So use the same strategy. 2 times 3 times 4 times 5 plus 1. So we're going to make a number now that when you divide it by 2, 3, 4, or 5, it's going to have a remainder of 1. So whatever number this is, when we divide by 2, 3, or 4, or 5, it will have a remainder of 1. Did anybody multiply that out and add the 1? Anybody get that?
121.
121. Is 121 prime? No, it's not. I heard both no. Anybody know what 121 factors into, or if it does not? 11 times 11 it is, yep. So it's not prime. 121 is 11 times 11. So the prime factorization of 121 didn't have a 2, 3, 4, or 5 in it, because if you divide 121 by 2, 3, 4, or 5, you divide and get a remainder of 1. But this does give us a prime. A prime larger than 5. So we have a way now to find a prime larger than any particular number. We just multiply the numbers together up to that number and add 1, and that will give us a number that's either prime or not prime. But if it's not prime, it has a prime factorization with a prime factor bigger than the number. So for example, find a prime larger than 8. Okay, so following our strategy, what would you do for multiplying? Anybody? In getting the pattern, what would you do to multiply? What would you write down? Do you know?
2 times 3 times 4 times 5 times 8 plus 1.
Yep, all the way up to 8 though, so include the 6 and 7. Yep, so 2 times 3 times 4 times 5 times 6 times 7 times 8 plus 1. So now we'll know that whatever this number is, when you divide by 2, 3, 4, 5, 6, 7, or 8, there's a remainder of 1. 2, 3, 4, 5, 6, 7, 8 don't divide into this number evenly. What do you get when you multiply and add that up? 40,321, thank you. And I think we'll use Google for this and find its prime factorization. Did anybody happen to do that? This factors into 61 times 661. Would add a long sieve of Aristophanes to find that. Well, that means that we found a prime larger than 8. It was in the prime factorization this time. So 61 and 661 are both primes larger than 8. So this is the pattern we're going to use, and we'll go ahead and write out an actual proof this time. So this is a proof that you'll probably want to practice periodically before the quiz, and maybe have some notes on your 3x5 card for the quiz. Prove that there are infinitely many primes. Prove that there are infinitely many primes. So what it is we let M be any natural number. Let M be any natural number. So this is like our 3, 4, 5, and 8. Okay, so M is any natural number. We need a prime bigger than M. We need a prime larger than M. Okay, so if we can find a prime larger than any natural number, then we're set. We've done our proof. So we're going to make our big number now. Let B for big equal 2 times 3 times 4 times ... times M plus 1. Okay, so B for big number, let B for big number be 2 times 3 times 4 times 5 times ... times M plus 1. B is bigger than M. Okay, so B is a big number. B is bigger than M. B is bigger than M. Well, B is prime or not prime. B is either prime or not prime. B is either prime or not prime. If B is prime, we are done. If B is prime, we are done. If B is not prime, it has a prime factorization. If B is not prime, it has a prime factorization. Let P be a prime factor of B. Let P be a prime factor of B. P is not 2, 3, 4, ... M. P is not 2, 3, 4, ... M because they don't divide evenly into B. P is not 2, 3, 4, P is not 2, 3, 4, ... M because they don't divide evenly into B. So P is a prime larger than M. So we found a prime larger than M. So we have proven our proof. We'll start class Wednesday going over this again because I know it's hard. Okay, so we'll go over it again and you can give it some thought in the meantime and see if it clicks for you. I'll see you on Wednesday.
I think I'm doing